Now think about this. 11 large catchments of the size 50,000 to 100,000 square kilometers, as diverse as they can be. However, see the amazing linearity between load and discharge. So what that says is basically load is equal to concentration times discharge. And the fact that you have this linearity, what that says is that the mean annual concentration of nitrogen does not change significantly from year to year. So from year to year, what changes a lot is the mean annual stream flow. So you see, for example, if you take any of these, right? So if you think the red data points, that changes from 0.1 meter per year to 0.6 or 0.7. So that's quite a bit because these are mean annual values. But the mean annual concentration doesn't change, so the mean annual load changes direct proportional to the mean annual flow. So what does that mean? What it means is now if I know what my stream flow is going to be next year, I have a fairly good first order estimate of what my mean annual nitrogen load is. So what does this concentration depend on? Well, it would depend upon land use. So if you have a lot of agriculture, that mean annual concentration would be greater. So here you see this kind of clustering behavior, right? You see there's one group which is kind of these values that have one value of concentration and the other group that has another value of concentration. So you have these two values of concentration. Same pattern we actually also saw for phosphorus, and I'll come back to that in a bit. So let's take this message from this figure that the mean annual concentrations we are observing is not changing that much. So then we asked, well, just this is a curiosity side that is this unique to nitrate? Is there something about nitrate? Well, in order to ask that question, we selected 3 large basins, the Missouri, the Mississippi, and the Ohio. And we looked at a bunch of constituents. So you see these 3 are the 3 basins. And here we have nitrate, here we have total Kjeldahl nitrogen, and here we have ammonia. So on an average, you see this very strong linear relationship between load and discharge. You still keep seeing that. Scatter is a little bit much more for ammonia, but ammonia has other issues, so because it has other sources, so we won't go into that right now. Then we looked for phosphorus and silica. So this is total phosphorus, orthophosphate, silica. Once again, very strong linear relationship. The strongest, though, of course, is silica. Then we looked at carbon. So this is bicarbonate, dissolved organic carbon, and particulate. Once again, pretty linear relationships. So the relationship between load and discharge is linear, but the slope of that line is different from every watershed and constituent. So we wanted to say, well, what does that slope depend on? We wanted to explore that question a little bit further. So what we did here, we plotted the load of bicarbonate along the x-axis. So bicarbonate, because bicarbonate reacts relatively less in the system. And on the y-axis here, we plotted loads of nitrogen or phosphorus. And what we found is when we did that, so now we've taken all the watersheds together and we've plotted one constituent against another. We found that all the watershed collapsed into these single lines. So these slopes of these lines is a function of the reactivity of this particular constituent as a function of the reactivity of bicarbonate. Once again, this very unique pattern in nature. And we've not, in this work, we are kind of at the stage we have found this pattern and we are asking why this pattern exists. We have not really used it in a model yet or delved further into it. Well, then we asked, well, is it about something about the Mississippi Basin that's created the pattern? Because for a long time we were thinking, well, maybe the tile drains too. So there was a colleague in Europe. We were talking to her and she said, well, I see the same thing. So this is hypoxia in the Baltic Sea. So she had data from a large number of countries around this area. We took her data and plotted them exactly the same way. And this is total nitrogen for Denmark, Estonia, Finland, Germany. So a whole range of European countries. And we see the same pattern. Their data set is smaller, so ours is about 30 years or so. This is about 10, 12 years worth of data. Once again, the same linearity between load and discharge. This intrigued us, and we were trying to find out. So whenever we see a pattern, our next thing along that line is we are looking for the process that contributes to the pattern, right? So process exploration is kind of then, to an extent, a bottom-up exploration. You need to know what the processes are. So we said, well, let's go at a much smaller scale. Let's go at the scale of a 500 kilometer square watershed. And at this watershed in Illinois, we had very good quality data. So when you're talking about the Mississippi Basin, water quality data is sparse data. Here, for example, we had daily data. So we took that data and we plotted, same graph, nitrogen load as a function of discharge. Once again, we see the linearity, same pattern. Well, then at that site, interestingly, in addition to nitrate, we also had data for atrazine, which is a pesticide that's also applied to agricultural fields. Well, so we said, well, since we have it, let's also plot it like this. By then, we had gotten so much into plotting load discharge that whatever happened, we wanted to plot everything as load discharge. Well, so atrazine is not linear, right? So if you look at atrazine load versus discharge, there's quite a bit of scatter. I wouldn't call that linear. So that intrigued us. What is it about atrazine that creates this pattern, and what is it about nitrate that doesn't? What is the link between the two? So what is the difference between them? Because we thought that that would be a window for us to figure out why nitrate does what it does, or why phosphorus does what it does. Well, the difference, one of the big difference, is that atrazine has no internal source within the system, and atrazine has a very fast degradation rate. So atrazine is normally applied April, May, and within 4 or 5 months or so, you don't see atrazine anymore in your stream flow. So whatever atrazine was there, either it degraded or it went into inaccessible portions of the soil, and you see it no more. So the next year when you apply atrazine, you would see again atrazine, but between those 2 points you wouldn't, right? So it has a small half-life in the system, and it has no internal sources. Nitrate, on the other hand, has both external source, which is a fertilizer, but it also has internal sources, because nitrate is generated by mineralization of organic nitrogen in the system. So nitrate is, we call these exogenous and endogenous sources. So an exogenous constituent is one that's applied externally to the system, like atrazine. An endogenous constituent is the one that is generated within the system, like silica or calcium, that's weathering products, right? So those are pure endogenous constituents. Nitrate is like a hybrid. So it is externally applied, but there are also internal processes generating nitrate within the system. So based on this, we hypothesize that decades of fertilizer application have created this legacy mass of nitrogen within the system that acts as an internal load, as a buffer, and creates this effective biogeochemical stationarity. So what is effective biogeochemical stationarity? So stationarity is a concept that's used quite a bit in hydrology about systems that don't change in time, right? So we say, well, this is an example of biogeochemical stationarity because the concentration is not changing in time over the last 30 years. And the reason is, over the last 20, 30 years, the nitrogen that you have applied to the system has been converted to organic nitrogen, and that's just sitting there. So whatever differences you're making to your application today is not really affecting what you're seeing in the stream. That's the legacy of what happened 20, 30 years ago. So if you make any changes in land use practices, there is a chance you won't see any benefit. Depends on, if you do riparian zone changes, probably you would see it faster. So it depends how long it takes to flush the system clean of its memory. And we don't know that. For phosphorus, it's also true. So for phosphorus, and on this, a lot of work has been done in the Everglades in Florida, where they reduced phosphorus loads from the pastures, And what they found was that did nothing to the phosphorus loads that they were seeing. Because once you reduce your input, the sediments which had accumulated phosphorus over decades was now the internal source of phosphorus. So this is a great example of human impact, how we have created these man-made systems that act now as sources. So taking this a little bit further, I said this was our hypothesis, right? We have not really proven it. But what we wanted to do is kind of look at more endogenous constituents and see if they really do show this biogeochemical stationarity that we are talking about, or in other words, we also call it the chemostatic response. A chemostatic response means the concentration is not changing with time. So this is data from LTER sites. So LTER is the long-term ecological research site which is funded, and there are a few of these sites along US which have very high quality data. So we took data from those sites and we plotted the same thing. So this on the right is the load discharge relationship for calcium, sodium and sulfate, and on here we have plotted concentration against discharge. So you see there is pretty strong linear relationship between load and discharge, and much stronger than what you saw before for nitrate, right? So if you think about these cascade of constituents, at one end you have endogenous, which are very, very chemostatic or stationary. The other end is atrazine, which is completely non-stationary, or it's varying from year to year. And nitrate is somewhere in between, where it is actually an exogenous constituent in terms of fertilizer, but it is behaving like an endogenous constituent because of human impact.